Today's lesson is going to be about trying to write some generic transformation rules for different types of functions. Understand this is not meant to be just transformations for linear or just for quadratic or just for cubics or something like that. The idea is, if you watched our previous lesson on parent functions, we went and talked about multiple different types of functions and their characteristics. Now, I want to write generic transformation rules that could apply to any of those 6 functions we talked about. Looking at this then, this is a generic equation that is meant to be able to be adapted to any of those types of equations. Understand the parentheses that you see here are simply meant to represent whatever the special thing is for each type of function. Meaning, if we apply this to an absolute value function, for example, these aren't parentheses, they would be absolute value brackets. If we applied this to a square root function, well then we aren't dealing with parentheses, it's everything inside the parentheses here, the bx minus h, would need to be underneath the square root. If this was a quadratic, well then yeah, we do have parentheses, it's just along with the parentheses we would also have an exponent right there of 2. If it's a cubic, that could be a 3 right there, right? It's that type of idea. That's how we're applying this to all the different kinds. So let's start with the a and b values you see here. I guess actually I say understand f of x is just your stand-in for your output, y, x is the input, right? It's the normal x you're used to seeing. So obviously those are not representing transformations. We have f of x and x in all of our parent functions that we talked about in the previous lesson. So we're looking at a, b, h, and k. Starting with the a and b terms, notice these are numbers that are being multiplied. They are coming before x, and they are multiplying. So basically what these are going to do is these are changing your slope. Your rate of change is changing how fast or slow the graph opens, or you could say how narrow or how wide the graph gets. Or the other terminologies that we use for them are stretches or compressions. Stretches or compressions. Now depending on whether that number is in the A or B spot depends on whether we consider it a vertical or horizontal stretch compression. If it's in the A spot, then it's going to be representing a vertical stretch or a vertical compression. The idea with that being, it's kind of hard to show here over video like this, but it's the idea of like if you could put a graph on something that is stretchable, like not a regular piece of paper, but something that is something you can manipulate, and think about grabbing on the top and bottom of that piece of paper, meaning the vertical axis, right, up and down, grabbing on the top and bottom and pulling and stretching. If you did that, the graph would look narrower than it did initially. Conversely, if you held on top and bottom and squeezed, compressed that paper in, you're going to make the graph look wider. Visually, what we're talking about is like if you think about a quadratic that we talked about in the past. A basic quadratic, we'll say, looks something somewhat like that. That's not a perfect drawing, but it's close. If we vertically stretched this graph, it would look something like this. Meaning, notice it's still a U shape, it's still the same overall shape, but it is narrower, it's opening up quicker. If we had a vertical compression, then it looks something like this red line. Again, notice it is still a U shape, but now it's wider. It took longer to keep heading up, it opened out wider. That's what we're talking about with a vertical stretch versus a vertical compression. So, if your A value, or I should say if the absolute value of your A value, because you will not have negative stretches or compressions. If we have a negative A or a negative B, that's a separate transformation. We'll talk about that later on in these notes. But you cannot have a negative stretch or compression. So if the absolute value of A is greater than 1, then you have yourself a vertical stretch. So meaning the blue line, for an example. If the absolute value of A is between 0 and 1, again, not negative, not a thing, but if it's between 0 and 1, so we're meaning like actual fractions, not improper ones, but regular fractions, like 1/2, 3/4, 2/3, things like that. If you have something like that, then that is going to be a vertical compression, which would be like the red line. Your B term is also, like I said, talking about stretches and compressions, but we refer to them as horizontal stretches and compressions. This is going to look like I'm giving you opposite rules of what I just did, because for a horizontal stretch, your B value, the absolute value of B, should be between 0 and 1. For a horizontal compression, the absolute value of B should be greater than 1. Now, this actually makes sense if you think about it for a minute, because if you think about when I was talking about grabbing, a stretchable piece of paper on top and bottom and pulling it, making the graph narrower, now think about that same concept, except if we're saying horizontal, now we're talking about holding the paper on the sides, the left and right side. Well, if you hold that paper, if you hold that graph on left and right sides and you compress in, you squeeze in, that's going to make the graph narrower the same way stretching it vertically did. A vertical stretch and a horizontal compression are going to effectively do the same things visually to the graph. On that same token, a vertical compression and a horizontal stretch are going to effectively do the same thing as far as visually on a graph. So we don't really have different rules here. It just kind of looks like they are opposites. But there is a common phrase in transformation lessons and algebra classes that you will hear: parentheses always lie. If you have had a teacher say parentheses always lie, that is a common phrase, because if you just memorize your rules for a vertical stretch and vertical compression and tell yourself that horizontals are the opposites inside the parentheses, you could do it that way too. Either way is fine, really, although I think being able to understand what's happening visually is probably a better idea. Moving on, let's look at H and K. H and K are going to represent your left, right, up, down shifts, your left, right, up, down transformations. Okay? Your K value is going to designate your up and down, and your H value is going to be your left and right. Meaning if you have a number being added or subtracted to X inside the parentheses, then that's your left and right shift. If there's a number being added or subtracted to the equation but outside the parentheses, that's your K value, and it's your up and down shift. Now K values do exactly what you would expect them to. Meaning if you have a positive K value, it moves up in the positive direction. If you have a negative K value, it moves down in the negative direction. H will seem opposite of what you might expect to begin with here. If you have X plus some number, it's actually going to shift the graph left. If you have X minus some number, it's actually going to shift the graph right. Now the reason for that is H is inside the parentheses there with X. So whatever is special about each function is happening to both X and H. Meaning when we talked about the quadratic earlier, both X and H are being squared. So if you think about me giving you an equation that say is like X minus 1 squared, well, the reason that's going to shift the graph to the right is because think about where the vertex for a parent quadratic is. For the parent function of a quadratic, the vertex is at 0, 0. So we know we were supposed to be getting 0 out of this whole parentheses. 0 is what's supposed to be being squared. Well, what X value right here would allow us to still have 0 squared? We would have to put a positive 1 in here so that 1 minus 1 gives us 0 squared still. And that's why seeing this minus actually means the graph shifts right, because it's not about this one here. It's about the one we would have to plug in to still keep it 0 squared. Now that may make sense. If it doesn't, my recommendation would be to actually play around with some graphing. Right? I don't want to make this video take an extremely long time, so I won't switch over to Desmos and do a whole bunch of graphing stuff, but there are a lot of great exploration activities for transformations. Just get on Desmos.com, get on a graphing calculator, play around with some stuff using this generic equation, and see how things shift. It will really help you figure stuff out. The last transformations we need to talk about would be reflections. This is where the negative a and negative b values come into play. If you have a negative a value, meaning the negative is effectively at the beginning of everything, that is an x-axis reflection. If you have a negative b value, meaning the negative is inside the parentheses with the x. So if it's a quadratic, the negative is being squared also. If it's an absolute value, the negative is inside the absolute value. It's inside the square root. If the negative is inside the parentheses, then it's going to represent a y-axis reflection. Let's take a look at this equation, this function, as an example. So if I want to find the transformations, we want to list out the transformations here. First, we have to determine what type of function this is so that we can compare its parent function to what we have here. Well, since I see this 2 exponent, that would make this a quadratic. We know from our parent function lesson that the parent function for a quadratic is f of x equals x squared. Meaning, I'm supposed to have a y, I'm supposed to have an x, I'm supposed to have an input-output, and I'm supposed to have that 2 exponent. So the g of x does not represent a transformation, the x does not represent a transformation, nor does that 2 exponent. Everything else extra here, meaning namely the negative, the 2, the 3, and the negative 7, these all must represent transformations because they weren't in the original parent function. So if we want to work our way through this, looking at the negative first, that's the reflection that we just got done talking about. If we think about what spot this is in, both the negative and the 2 are in the a value spot because they are outside the parentheses at the beginning. They're multiplying to stuff. So those are a terms. If we have a negative a term, that is supposed to represent an x-axis reflection. The 2 then is its own separate thing. The 2 is going to help us determine whether we have a vertical stretch or vertical compression. We do know right off the bat that it's vertical because, again, it's in the a value spot. If it was inside the parentheses but still before x, that'd be a b value. Then we'd be looking at horizontal stretches or compressions. Remember, we want to look at the absolute value of this. It's not a negative 2. We're looking at it as just 2. 2 being greater than 1 means we would have a vertical stretch here. It's a vertical stretch because we are looking at it as just a 2. We're taking the absolute value, which means we're just looking at a positive 2, and that's greater than 1. Next up, we've got 3, which is in the h value spot. Remember, it is somewhat the opposite of what you would expect it to be, another reason for the common phrase of parentheses always lie. Even though it's plus, we think about that would require a negative 3 for our x value to get it back to the 0 it should be for our parent function. And so it's actually moving in the negative direction left 3 units. Finally, this negative 7 is in the k value spot because it is being added or subtracted, but it is outside the parentheses. And so signs actually make sense for that. If we're deciding between up and down movement, down is the negative direction, and so since this is a negative 7, it means we will shift down 7. That's how you can use these rules to find transformations without even having to graph.